My name is Alex. I'm from University of Illinois in Chicago. I'm working with Professor Daniela Tuninetti and Professor Natasha Devroy. And the topic of my presentation, or my poster, is the mixed inputs for two-user Gaussian interference channels. So in this work, we develop a necessary machinery to analyze performance of discrete or more generally mixed inputs in Gaussian interference channels. And the end goal of this is to actually study capacity of interference channel. So the capacity of interference channel is still an open problem, even though it's well understood. For example, the Hanin-Kobayashi scheme is within half a bit of optimality, but it is not clear that there is no proof that Hanin-Kobayashi is actually optimal. So to that end, we chose a different attack, and what we're going to look into is actually a different coding scheme as opposed to Hanin-Kobayashi. So let me give you some useful bounds that we will use in this work. So one of the bounds is the generalization of the Ozaro-Wiener bound. So what this says is this is basically a lower bound on the rate of a point-to-point channel when we use discrete inputs. So what it says is that this rate would be the entropy of the discrete input minus this gap term, and this gap term is a constant minus a term that is basically as a function of a minimum distance. So a minimum distance between 2 points. So for example, in the case of PAM input, or equidistantly spaced uniformly distributed random variable, we know that the entropy is log n and the minimum distance is of this form. So the idea would be to use this bound for a multi-user system. So in the multi-user settings, what will happen is when we use two discrete inputs is that we will have a sum set. So we would have to compute, so in order to compute the entropy, we would actually need to know what the cardinality of this sum set is and what the minimum distance of this sum set is. So bounding cardinality or computing cardinality is not that tough, but minimum distance is actually tougher. So for example, this is a plot of minimum distance as a function of one of the channel gains. So you see it's a very irregular function in one of the channel gains. So in order to bound it or to compute it, we have the following two propositions. So you see the way the minimum distance behaves is that there's this irregular part and then there's this regular part. So what the proposition 2 says is that in this regular part, the minimum distance behaves as a minimum of two minimum distances. And the proposition 2 says that the minimum distance behaves as this function, so let me start over. So what this proposition deals is it bounds the minimum distance in this part, but you see that at some points the minimum distance is actually 0. So the true bound is actually 0, but what we can do is we can exclude some of these points and I have a bound that holds almost everywhere on a set of a measure close to 1. And this is the bound. So basically the way the bound behaves is that the bigger we make the set, the lower the bound, or the more points we include, the smaller the bound becomes. So with these tools in hand, we will apply it to a problem of an interference channel. So we actually know what the capacity of the channel is. It's this multilateral expression. Unfortunately, it's uncomputable, so in the sense that we don't know what the maximizing distributions are. And it's actually not even clear that this form actually has a single lateral expression. So for example, it does in strong interference, but in all other regimes, we actually don't know it. So one thing we can do is to look at the inner bound of this problem, which is attained by considering IID inputs and getting rid of the convex Hall operation. And this bound is the so-called treating interference as noise bound without time sharing. So what we will show is that this bound is actually, this inner bound, which treats interference as noise and doesn't use time sharing, is actually very close to the capacity. So what I mean by very close, we will use two different metrics to do this. One is the so-called generalized degrees of freedom. So what this studies is it studies capacity at high SNR, and what happens here is we take the achievable rates and we scale it by, we divide it by point-to-point capacity and take SNR to go to infinity, and INR would be a function of SNR to some exponent. So if alpha is less than 1, the interference is weak. If alpha is bigger than 1, the interference is strong. And another metric we will use is the constant capacity within a constant gap. So what we will do is we will show that this inner bound is within some constant away from the best known outer bound, and that gap is independent of power and channel parameters. So it's a universal gap. So here's our results. So in terms of generalized degrees of freedom, this inner bound and the capacity is actually equal. So what this says is that in terms of treating interference as noise without time sharing is actually optimal from generalized degrees of freedom sense. The second result is a more robust result, and what that result says is that treating interference as noise and without time sharing is actually within a gap. And so these are the gaps for each regime, so for each regime they're different. So again, the proof consisted of using these so-called mixed inputs and applying a Ozara-Wiener bound that we generalized on the to this, basically on the mutual information in this bound. So the nice thing about this treating interference as noise bound is inner bound is that it works for a lot of different channels. So it does. So for example, one of the channels it works for is the channel with partial codebook knowledge. So this is a channel where decoders are restricted in the possible decoding schemes that they can do. So for example, they cannot do joint decoding or successive interference cancellation. And what we show is that this inner bound, since this inner bound applies, what we show is that the loss in the when the receivers don't know codebook, that the loss is at most 3.5 bits. So not knowing codebook is not that bad. Another channel that we applied it to is the so-called block asynchronous interference channel. So this channel is actually information unstable, so you cannot even write out a single letter expression for it. But this bound still holds, and the known outer bounds hold, so our results naturally apply. So thank you.